Hi, welcome back. Hope you had a good lunch, coffee, dessert, coffee, more coffee, and a great poster session. Yeah, thank you all who presented in the poster session. The posters were quite amazing, and we found the shade for you, so that was also good. I am going to introduce the next speaker, and please stay after the talk. We're going to have a panel discussion, which is really a way for us to let what we heard today sit and talk to each other and wrap up the conference with that. I'm pretty sure there was quite a bit of food left over, so there might be some when you go out. Feel free to take what you want. And well, without further ado, let me introduce our next speaker, Jesús de Loera, who is a 2021 Advanced Awardee. He got his bachelor's degree. We usually don't say bachelor's degree, but in this case, it's from UNAM, and that's my alma mater, so I have to say it. We have that in common, in addition to both being professors here at UC Davis in the math department. He received his PhD in applied mathematics from Cornell University, and Tom pointed out that each one of our speakers today had a Cornell connection, so that was very interesting. And I am ashamed to say that I've never been to Cornell, so maybe there's something there I need to go visit. He did postdocs at the University of Minnesota and at the Swiss Federal Institute of Technology before arriving to join the faculty at UC Davis in 1998. Jesus works at the intersection of combinatorics, discrete mathematics, optimization, and computer science, so very interdisciplinary work. And I think we saw that as a common thread today. That to really, in a way, to make progress, you need to pull from different areas and be open to different ideas and different perspectives. He has published many, many papers, 2 books in computational mathematics. He's fellow of the American Math Society, of the Society of Industrial and Applied Mathematics, and he has won multiple teaching and mentoring awards. The most recent is a Distinguished Teaching Award from the College of Letters and Science in 1918, but before that he received one from the Mathematical Association of America. He received the Chancellor's Award for Outstanding Undergraduate Research Mentoring in 2013, the Principals Community Award in 2006, and he was a Chancellor's Fellow in 2003. More recently, he's been leading an effort to create a national network of Latinx mathematicians. Thank you so much, and we look forward to your talk.
All right, let's see. Doesn't recognize my face. There you are.
That was the same picture that was used to advertise the chemistry. Here at Davis.
Yes. All right. Well, thanks so much for the opportunity to speak to you. I am aware that this is the last talk of the day, so I will try to make it more entertaining, light. And in some sense, everything new that I'm going to say is joint work with young people. So young people for me are very important. So I would like to say, I mean, some of you have seen the poster of Felix. And some of the papers that I'm going to mention here have to do with all these wonderful people that are here. And some of them are in the audience. I'll mention more. OK, here's the menu for my talk. So first, I want to start by acknowledging that artificial intelligence is happening. And it's changing. The amounts of data and information we deal are massively growing these days. So that is really a kind of the big elephant in the room. But I have 2 approaches to this revolution of data and artificial intelligence. The first is that there are problems that math can solve. And I will talk to you about examples of the work that I have been doing on my group, on how geometry in particular, so some people don't think as geometry as a very applied part of mathematics. I mean, you might think of differential equations, probability as very applied, but I claim that there are interesting geometric questions inside data science. And I will try to show you that math can help data, understand data. But I want to make a point, a very important point, that there's limitations for what we can do with mathematics and science. Let's say the technical things we can do are limited. At some point, ethics and fairness and inclusion and equity have to come to help really make artificial intelligence the right thing, the right object, the right field. Yeah, so artificial intelligence is transforming our life, presents many opportunities, and again, I will emphasize first the mathematical challenges and then the technical challenges. So the first half, the first part of my talk will be a bunch of examples, hopefully not very technical examples, of the kind of questions. I'll give you just a taste of the kinds of questions that we explore. I promise not to be very technical, and then I will go into some of the serious ethical concerns. Okay, so let's start with the math examples. So I have, I believe, 4 examples. And I want to start with acknowledging that maybe some of you have never seen, so you have heard of machine learning, you have heard of artificial intelligence, but you may not have seen this before. So let me give you a crash course on machine learning, or at least the way I think about machine learning. So here is a very concrete situation. You have pictures of dogs and muffins. And the challenge is to teach a machine to very quickly classify, to tell apart the muffins from the chihuahuas, right? You have muffins, and as you can tell, some of the chihuahuas really look like the muffins. It's not so, even for a human, you might eat a chihuahua by mistake. So you got to be careful, right? Okay, but not only, I mean, we don't want humans to be doing this, we want machines to be doing this. So what's the framework of a machine learning to tell apart, tell apart the muffin from the chihuahua? So the framework is actually to use mathematical analysis and to create some kind of function. So there will be some mathematical equation or a function that will separate the 2 types of data. So let's say you have a magic function f, which is a classifier that if a picture of a chihuahua comes, it's going to say 1. And if a picture of a muffin comes, it's going to say 0. Essentially, it's going to just say yes, no, right? Okay, so that's the gist of the idea of machine learning to compute this. So first of all, for me, okay, first of all, let's forget about the meaning of these pictures, right? So for a machine, these are just zeros. I mean, these are pictures. These pictures are pixels, which are matrices full of numbers, most likely zeros and ones, or maybe the intensity and the color have another meaning. But these are high-dimensional matrices or vectors. So again, geometry. I like to think of this in terms of geometric ways. You have the red points that are the chihuahuas, the blue points, and this function in high-dimensional space is going to separate the reds from the blue. And if you're classifying other types of information, it's not going to be pixels. Maybe it's going to be medical data. So that might include, I don't know, temperature, age, and weight, and other things, right? So, but that's the principle. So a classifier is a function f that, again, can tell just by the sign of the function. When x is my matrix that represents my chihuahua, I plug it into my function and I say, oh, it's positive, it has to be a chihuahua. Or if it is negative, it's a muffin, right? So, but again, the way that you may have heard already the terminology training data. So typically a bunch of humans will tell, tell the machine, this is a chihuahua, this is a muffin, etc. Right? So you give a bunch of data points that are here. The data x1, xn. These are the matrices that represent those pictures, and then you have labels y1, yn that represent 0, 1 if it is a chihuahua or a muffin, right? And again, xi is a high-dimensional vector, so it has d entries, the vector of the matrix. But think of it that d is very large. And now the labels are just zeros and ones. And now, again, I would like to find f. And the general strategy is you find a function that minimizes the mistakes on prediction, right? So you feed this data to the function, and then you try to find the function that minimizes the mistakes on the classification. So if you have never seen this before, it might be, in the case of the Chihuahuas and the muffins, there's a very popular model called logistic regression that essentially assumes that the probability of being a Chihuahua or a muffin follows a logistic function. So it looks something like this. Let me just draw a logistic function for you here. So you have the axis, let's say, so maybe it goes something like an S shape. Yeah, in such a, you should interpret this that if you are in this region, the X's that hit this region, you will get likely to be a Chihuahua, and the other one will be the muffins. So it's a yes or no type of function, right? So this is the assumption. We're making an assumption. When we have models in mathematics, we make assumptions, and this might be good for your data. I mean, often this is a very popular model because a lot of real-life situations follow the logistic regression. But remember, we know X. We know X and we know Y. We know the label and we know the pixels and the matrix. So what you are trying to find, what you really are trying to find is the beta here and the W here. These are the parameters that we don't know and we normally run. So if you have taken a class in statistics, I mean, you know, run a regression and you find these numbers. Now, when you run a regression, you are supposed to minimize something. And statisticians love to minimize the log likelihood estimator, right? So here I'm showing you just the function. So again, we know the x's, we know the yi, the xi's, the yi's, and the parameters w and beta are what is going to tell you what the logistic regression function is going to look like. But you need to solve that as an optimization problem. You optimize and find the one that minimizes this. Okay? Okay, that's great. This is a very, very nice principle. Now, I'm a mathematician. I work in a math department, so I would like to actually understand the details, let's say, of using these models. And one of the problems we find with these models is that you have to solve an optimization problem to find the model, to really use the model. But there's a little problem. The optimization problem may not have solutions. This is something that in statistics sometimes people just take for granted, or maybe in applications you sometimes say, oh yeah, we run this regression and we get something. But what people are not completely aware sometimes is that the models may not reach a solution. There's no optimal solution really unless some conditions are satisfied. And a lot of my work has been trying to understand when it's legal to run the models, because maybe the models are giving you nonsense if you don't have the right conditions. So let me give you just an example of the logistic regression. So it turns out that when you have just muffins and dogs, you can do you can run the logistic regression. It will exist. The correct optimal solution will be existing, guaranteed to exist, when you actually have some overlap on the data. So there has to be sufficiently many data points that the blue points, so let me actually do it with some real colors here. So you have, these are the Chihuahuas, and then the red points are the muffins. I don't know, so you have some red points. So if you look at the smallest polygon that contains the muffins, so that's some kind of polygon like this, and you look at the smallest polygon that contains the Chihuahuas, they have to overlap at least a little bit in order for the model to guarantee for existence of the model. And this is something that is often forgotten. So in some of my work, I have been interested on for example, how many samples, how many data points do I need to be guaranteed that I can be with high probability be sure that this happens, right? We are talking about sampling probability events. So maybe all I can do is predict or do an expectation. So if I sample 100 times, can I expect that I run the logistic regression and my problem will have a solution? Can I do that? So that's one of my papers. We have been working on this type of problems. How many samples do you need for logistic regression or other models that you use to to really be correctly applicable. For example, in this particular case of the muffins and the chihuahuas, that you need to really sample at least twice the number of features of your logistic regression problem. So for example, if your pixels, your photograph is 120 pixels by 120 pixels, something like that, well, you need to sample 120 square points in the data to expect that something nice will happen in the logistic model. So is the first problem clear? Is everybody with me so far? Okay, so that's the first type of problem or type of work I do, trying to understand when models make sense, when they are legally usable, right? Okay, wake up. If you didn't understand any of the previous example, let's look at a different example. This is, if you like bird watching, here are some birds that I believe all come through Davis at some point or another. I think we made sure to have this collection because these are birds that do come to Davis, maybe not all year round, but some parts of the year. And anyway, so you go bird watching, and there are M types of birds. So you already know that in Davis, maybe there are 10 types of birds that come through the season, okay, the winter season perhaps. And you want to go bird watching, and you want to be sure that go enough times to watch all the birds, okay? So the question that I'm asking is, how many times do you need to go bird watching during the season such that with high probability you will get to see all the birds? So let me try to tell you what the issue is here, right? So the birds come randomly. So the birds are coming to you randomly. So you go on Monday and you see, oh, there's a geese. And then you go again on Tuesday, oh, there's another geese, right? So you start observing the birds and you see the birds, but they might not come, all of them, in sequence, right? You might get lucky and see all the birds in a sequence of M days, let's say, or M observations, but that's not always the case, right? So I'm interested to try to help data scientists, people that collect data, to have some kind of estimate of how many observations do you really need before you can guarantee sufficient amounts of data. So I can tell you the answer in this case under the assumption that all the birds come with equal probability, okay? If all the birds come with equal probability, I need to go bird watching about M log M times, yeah? M times the logarithm of M. Many observations need to be performed to be fairly sure, let's say, with probability 1, you have observed all the birds, okay? That's a very, very beautiful observation, right? Now, but again, I made an assumption. Models in real life make assumptions. And the assumption that I'm making here is that, that the birds come with equal probability. And that's far from the truth. I mean, for example, let's think about geese. If I say geese, and I tell you, let's go in June, you're not going to see a single geese in Davis, right? I mean, we know that the probability is a more complicated function, right? The likelihood of seeing a particular bird is actually a function of the time. It's a function of the time. It's not constant, right? So these types of problems, I'm very interested. That's the kind of things me and my students work on, trying to make predictions of these complicated problems. And you can ask all kinds of similar questions. For example, what is the best day to go watch? Like, for example, you can only get away from work 1 week. Which week of the year should you get away? You know, assuming that you are a very well-planned person, you are very organized, and you study the probabilities of all these birds in advance. So what is the best, most likely week that you will go and all the birds are there? So let's say all the species of birds appear in that time. By the way, this can be applied not just to birds. I'm giving you the example of birds because it's a nice, easy to understand example, but you can imagine this can be applicable to other kinds of sampling situations, like, yeah? Are you with me? Did everybody understand this type of problem? So again, it's the type of question where, do I have sufficient data to make conclusions, right? And math can help you with this. Okay. Yeah, by the way, these are geometric problems, even more when you do this in for example, imagine that it's not just when you went to see the bird, but where you went to see the bird, right? There's the probability distribution depends. I'm watching the birds in Davis or in the Bay Area, so that there's some location or geographic information that is necessary. Okay. Challenge number 3. If you didn't understand any of the other challenges, let's see whether you understand it, you like this challenge. I really like this challenge because we deal with a lot of uncertainty in data, especially in applications. Yeah, I mean, you will see the type of application that I'm interested. So imagine that there's a chemical spill. So there's, let's say, oil spilling on a certain region, certain coastal region. So containment is very important. So I don't know if you have seen the pictures from oil spills, but they put these, how do they, I mean, they really look like barriers. They look like barriers. So essentially it's to try to contain the spill in a location, right? Now, if the chemical is very obvious, maybe this is easy to do because you can see it's black, oh, it's black with oil or something. But imagine a chemical that is not so easy to detect by the naked eye. You need sampling to know where the chemical is. So imagine that there's a chemical. I mean, you can also think actually landmines. That's another application. You can think of landmines. So there's a region that has been, unfortunately, is dangerous. You cannot go there. You want to try to understand where the landmines are. Essentially, this is a region that you don't know the border of this region. You just know there's a bad region there. So, and the only way you know how to try to find this region is by sampling. So you're trying to learn, you know, machine learning is about learning. You're trying to learn the shape of this region by just sampling points inside this region. So imagine that you can do something like this. I can take samples. You know, I can take samples and I can say, well, some samples are definitely don't have this negative chemical, or they're good, and some samples will be bad, right? So I'm very interested on trying to find a containment region. So imagine that you want to find a containment like a circle or some kind of ellipsoid that contains 90% of this chemical. So this is kind of the prediction of a containment region. And again, all you can do is sample. So you take the sample and say, yes, definitely the chemical is here. Let's count that in. And you sample and sample again. So the question is, how many samples do I need to make a prediction? And even better, so I would like to make a prediction of the bad points. Let's call them the bad points because they come from a chemical spill. So I would like to predict where the bad points are. And I'm allowing you to catch, let's say, a failure of catching I give you a margin of error. So let's say you need to catch 97% of these bad chemicals. I allow you some flexibility, let's say, 3% of flexibility. And I also want to have another probabilistic measure of trust, and I call that delta. So this is in some sense your confidence level, and this is the guarantee of the quality. You have epsilon is the quality of the sampling, of how much you took away the bad points. And then you have delta is you can go back to the authorities and say, I'm confident that if we do this, we can actually get some kind of trust region. So it sounds kind of interesting that what you can do. So let me tell you what's the approach. So what do people do in practice? Well, you pretend you already know the answer. Essentially, you pretend you already know the answer. If you already know the answer where all the points are, then I could actually find the circle. So imagine that my points look something like this. I can actually, there's very simple, fast algorithms that will tell me the circle. They will find this circle that contains all these 97% of the points. I can do that. But I don't know these points, right? All I know is sample and sample and sample. And so what I do is essentially I run a sampling algorithm. So I sample n times. Capital N times. So I sample n times. These are my samples. and I run the prediction with those ensamples. It's an approximation. It's a prediction based on the samples that I got. Yeah? And the question is, how many samples do I need to guarantee that my prediction, my approximate prediction is pretty good? And we have theorems of this kind. So I don't want to put a lot of theorems. Mathematicians, we might actually just write theorem after theorem after theorem. I'm just going to show you one here. Again, you have this tolerance so you're willing to sacrifice epsilon percentage of error, and you want some kind of measure of trust of the answer. So we were able to write some kind of bound just on the types of problems we're working, because they have a mathematical property called convexity, so we can actually use that and solve this problem in this case. And this has a lot of applications where you don't know anything about the distribution. See, that's something that I always tell my colleagues. Most people, sometimes we talk about probability distributions or models, mathematical models. But in real life, when you go talk to the engineers or the McDonald's manager, when you actually talk, they don't have distribution. You tell them, is your distribution Gaussian? No, they don't even know that, right? They just give you the data for the last 10 years and deal with it, right? This is what you have to deal. Anyway, so that's the other challenge. Are you with me so far? Everybody, okay? Okay, I actually want to go to let me just go to the other challenge, because I want to get to the other part of my talk. So I mostly work on more foundations of data science, foundations of algorithmic mathematics. That's what I do. But recently I have been doing a collaboration with the vet school, with the advanced imaging facility at the vet school. So our collaborators, Dr. Ingrid Bruce-Masher and Dr. Colin Reardon. So the advanced imaging facility, they help people across campus. I mean, the medical school, the vet school, chemistry department, I know they help some people on trying to do imaging of biological samples and other, Ingrid is here. She can tell you more about the use of the facility. Anyway, so what we are trying to do is to transfer new mathematical methods to understand very complicated images that they get from their microscopes. They have fancy microscopes, and they get images, 3D images, not 2D images. So we're not talking about, like, for example, there was a poster that is essentially projections of cryogenic, right? You project with the electronic microscopes. These are really three-dimensional reconstruction of three-dimensional images. So, but again, we want to specialize in things that have very complicated morphology. And we found a problem in neuroimmunology that is right on the type of mathematics that we have. And we are hoping to make a lot of neuroscientists happy on campus. So let me tell you what this is. So I apologize if you are a biologist, and I'm going to say something wrong, but just hang on here for a moment. So we have microglia. So inside the brain, and it's not just humans, but also all kinds of mammals, I believe. There's these cells that are essentially parts of the immune system, but they are in the brain, or the neurological information. And these new microglia are in the entire brain of organisms, and they help detect damage on tissue, if there are pathogens and things like that. Now, the way they look, I'll show you a picture in a moment, but the microglia look rather complicated. So they are three-dimensional, and they look like trees. I think it's better that I just show you a picture, because once you see a picture of a microglia, it's better to understand. So I don't know how much you can, it's a bit dark, unfortunately. I apologize. Well, I think you see the white, the rendering that you see here this is the correct, in some sense, the correct answer. So these are microglia. Look at how they complete. I'm talking about three-dimensional picture here, okay? And the microglia look like these branching trees, or like roots of some tree. And they are very complicated. They intermingle. And we are supposed to reconstruct these images. So they take the image, and we are supposed to select these are the right cells. What I'm showing you here is a picture that, so the middle picture, so this is the input, in some sense. Here is in the left is the input. Sorry that is not so visible. In red, you see the microglia. In blue, you see the nucleus of other cells. And this was a prediction of some software called 3D Morph. They predicted this, but it's incorrect. So what's the problem? That 3D Morph predicts some things are microglia that are not microglia. And biologists know that because they don't have a nucleus. You cannot have a cell, a live cell, without the nucleus, right? So for example, here, you can see that there's some junk. All this junk here was removed by the biologists, right? Like manually removed by the biologists. So we are trying to compete with 3D Morph, with some of these. We have a new software we call PrestoCell. It's coming up to be released very soon. You are the world premiere of PrestoCell here. So PrestoCell is essentially doing image segmentation on very complicated cells. We have been focusing on microglia, but this, in principle, the same mathematical methods can be applied. So the mathematical methods we use is actually topological data analysis. There were some posters in topological data analysis. I believe we have at least one, no, maybe two posters in topological data analysis. Yes, that's right, from the Arzuaga Vasquez lab. Anyway, so essentially what you do is use topological data analysis to reconstruct the shape, and then we have our brilliant inspiration was that, okay, the problem with the microglia is that they're so irregular that it's hard to tell where they begin, where they end, but we have the nuclei, right? So we have the nuclei. And the nuclei are nice. So you can see the nuclei are more roundish. You can see in this picture they look more round. So we use the nuclei of the cells to try to tell where the cell begins and where the cell ends. And we make a prediction. You can see the final prediction of the software here. And now, even better, and this is the part where we still need to use humans. So sorry, I'm showing you here the output of the software. And the software produces a recommendation for the expert human, a recommendation for the biologist. It doesn't pretend to be completely correct, because we think we came to the conclusion that's not the right way to do things. It comes to a suggestion to the user, and the user then says, well, I don't believe this blue part. I don't believe this blue part is actually in the cell. We should probably not take that. So they can remove let's say portions of the picture or conglomerate parts of the picture so that the experts have an input on this. So now in a future, let me just say the following. In a future, we hope that this step, a machine can learn from the expert, hopefully, and do predictions based on machine learning, that they can learn, the expert conglomerates these kinds of groups. Maybe the machine can do that. For now, we use topological data analysis, which is a non-supervised method in machine learning. It's an unsupervised learning. Make a prediction, and then we give the ability to the user, to the biologist, to the neuroscientist to make the final decision of what is the correct thing. And that's the tool that you see here that was developed by Jue Wu. He's a graduate student. I don't know, I don't think he came today, but he's a graduate student from the CS department working with me, and we have produced these kinds of predictions. All right, are you with me? Everybody's with me? All right, I'm going to, if you didn't understand anything I said, hopefully you will have a chance to, the last part of my talk is more philosophy, I will say, or more ethics, a little bit of what I feel is happening in the field of artificial intelligence, and I'm sure some of the things I might say might be controversial, perhaps, or you don't agree, and I would love to hear what you think about these things. But my opinion is that artificial intelligence definitely is going to change things. and mathematics is the foundation. So let's say science is the foundation. But I believe it's arrogant for some mathematicians may say, or computer scientists may say, oh, just let us do our research. Just leave us alone and we'll do great things, right? I think that's arrogant, and I'm very scared sometimes when I hear famous computer scientists talk about that way. I think that math alone cannot possibly fix all the problems of artificial intelligence, and there are plenty of problems that need to use ethics and the humanistic perspective, diversity, inclusive perspectives are necessary to make a correct solution of these problems, and I would like to mention a few of them, okay? So so this is a more philosophical discussion if you want. So let's go to the first part, and this is the problem of biased or incomplete maybe data. Essentially here I'm showing you just one example that has made the news, and that is face recognition. So face recognition relies on sufficient data, but we have seen in the news, unfortunately, the data that is provided for face recognition is rather biased. So unfortunately, there's a lot of, let's say, Caucasian or white faces, but not enough African-American faces, and that leads to terrible, terrible problems. So it cannot even recognize many famous people, right? So that's a terrible problem. And yes, there's also issues with face recognition and privacy. Like, you're being monitored. If you go in public places, your face is being scanned maybe, and things like that. But in this particular case, my concern is something even more basic. That when somebody is creating a face recognition software, and they don't train with sufficient data from all groups or from a representative demographic sample, you don't have enough data, but not enough in the sense that it's really corresponding to the distribution of California, for example, then you really are getting into trouble, that your conclusions and your software is going to act biased. If you feed biased data, your software, your algorithms cannot help it. They're going to be biased, right? So that's one issue. Okay, this is a serious one. Let's start with this questionnaire. Which one of these two pictures is real? Which one of these two pictures is false? One of them was created by a machine, and the other one is a real picture taken of a human. Okay. How many people think this person is real? Okay. How many people think this person is real? Okay, I think.
How many people think neither of them are?
Yeah, maybe. Yeah, some people think nobody's real. Yeah, that's a good point. In fact, actually, yeah, in this case.
I don't think everyone voted.
Not everybody voted, but I think I got the feeling just by quickly raising of the hands that more people believe this is real, right? I think that was my impression. Anyway, this is real. This is actually a real person. This is not. And one of the giveaways that you need to start. Does anybody know what the giveaway is here? Yes? The fingers. Machines get totally wrong the number of fingers, and therefore they blur. When they don't have enough information, they blur it. So you can see that the hand here is not clear how many fingers. You see, there's something weird with that hand. It's actually what, yes?
Don't they also look at the pupils to see if there's reflected?
Yeah, so that's another way but you see, for example, you're too far away to even look at the pupils, but the hand is a really quick giveaway, right? So it's something that we need to take into account, because you people are going to be having to face this question over and over again. I mean, you're going to have to maybe get a picture that, oh, this is my uncle calling me, or what's going on, right? We have seen videos. Have you seen videos of Obama saying crazy things? People are making this happening now. And so the issue is that we can, the fast production of artificial images based on training data is going to create some serious issues of ethical kind and misinformation. You can have very realistic pictures of somebody saying something outrageous, like Biden saying, I can jump and fly, I don't know. So that's really a serious issue. And there's nothing I can do as a mathematician alone to prevent this from happening in some sense, right? I mean, at least I don't know a way to do it. And this is an interesting question. Where do you need to enroll the government or regulatory agencies or maybe Congress to start thinking about laws about this? So let's go to a similar one, similar issue. This picture here is a picture that was generated. It's an art. This was just considered art. Okay, so this is art. You ask your machine to generate the picture of a woman reading a book over the darkening sky or something like that, right? So and the machine produces this beautiful picture. It's a really nice picture. Now, this was done by a generator, like an automatic generator of these pictures, but it's trained on many other pictures, right? So essentially the problem is that artists are getting their art stolen. Artists are, they download, somehow companies download their art, they use it to train, and now you can ask questions to this machine such as, produce for me a picture of Titus in the style of Picasso 1950s. And they do it. I mean, they really do it. So the problem is that this is affecting young artists. I mean, this is really a serious problem for young artists that are getting their art ripped off. I mean, that they get copied and they cannot compete against this machine producing lots and lots of pictures, right? Anyway, so that's ethical. Where is the data coming from? Because this is a very important issue that I want to raise. The data out there, if somebody uses your pictures or your paintings to train the machine, is that okay? I mean, can anybody just grab things? That's not good, right? So it's copyright violation most likely. But this is not decided. We're in a moment in history where many of these things are not really understood. Now let's go to another one that I really, really like to bring up because it's a recent issue from Nature. This guy, Arthur Sperling, he wrote a very nice article in Nature. I recommend you read it. But essentially the gist of the article is you have corporations, large corporations like Microsoft, Google, etc. They are training their models, and they don't tell you, they don't tell the rest of us what are in their models, what is the data they're using to do the training, right? And that's a serious issue because if you don't know the training data, how can I check that they're not doing something really illegal or irrational, right? I mean, really crazy. So again, this scientist, he's actually a very interesting person because he works in political science, sociology, social sciences, and at the same time, he's a data scientist. And he proposes that the solution to this is open source, that we should all have some kind of open source of training data that let's say corporations, universities, everybody that is interested in training models should have access to this. Are you with me, everybody? Okay, so. Okay, I'm almost to the end of my presentation. I want to leave lots of time for discussion. Maybe we can even start the panel earlier. I was thinking that maybe this will lead to some other questions as well. Who hasn't heard of ChatGPT? Everybody, unless you have been living under a rock for the last year or so, you have heard of these large language models that can talk to you and answer. For example, they can write school essays. They can easily write essays about Shakespeare, Hamlet, whatever. This is a real problem for people in the teaching humanities these days. They're very concerned about, people teaching high school also, right? Everybody's using ChatGPT. I read that there's even wedding speeches being written by ChatGPT. They just ask ChatGPT, please write a wedding speech for my wedding. Some of these applications are ridiculous, in my opinion, but there are some that I find myself very, very, very useful. And one of them is code generation. Simple code can be generated by ChatGPT. These are not incredible software, computer programs, but they are useful. And you can do that in almost any language. Like the other day, Some of you may know MATLAB. I mean, MATLAB is very popular in engineering and science. You ask to write a simple program in MATLAB, and it will do it right. And this saves me, I don't know, half an hour, 20 minutes of my time easily, right? So this is great. And also, I'm not a native speaker. You know, I come from Mexico. I don't have the knowledge to really get perfect English statements, but this thing can summarize, can simplify the text, can fix mistakes of grammatical kind. It's very useful. And but the problem is that it also leads to some really bad things. Have you seen this ChatGPT can lie about references? So you say, oh, give me a reference for what you just said, and it makes up stuff. And most recently, it said that some law professor in some university, I forgot where, was accusing this person of harassment. Completely false. I mean, it's just completely unfounded. And anyway, so this is very serious with the creation of these. So first of all, I don't think we understand, because OpenAI, the company, doesn't let us see what they are doing, right? We don't understand why ChatGPT is acting this way. But we have to be careful with this misinformation that is creating. Another issue that I really think is interesting is you must have seen that Elon Musk and many other people wrote a letter, a public letter, saying that all the companies doing AI should sign a moratorium on research. That in some sense, for 6 months, we should stop doing research on artificial intelligence, right? It's something, you have seen this because, and the concern they cited is that essentially they want to have enough time to prevent that AI is going to become sentient and essentially destroy humans, right? I don't always agree with Elon Musk. And in this particular case, I don't agree that, I find that it's more alarmistic to start worrying about, is Terminator, you know, for those of you who have seen the movie Terminator, are machines going to start killing all of us? I think we should already worry about things, simpler, basic things, such as, why is the data that they're using biased? Why is the data that they're using misogynistic, racist, horrible? I mean, like, what data are they using? That's an even simpler question. And I'm not really thinking about regulating the research, but we should probably think about regulating the products they're producing, for sure. By the way, regulation right now is all over the place. The US pretty much is whatever, we don't care. The European Union is getting very strict. They have a lot of rules and regulations. Some of them are so strict that it's hard to imagine they will be able to enforce it. China, for example, they pretty much say, well, we regulate from the point of view that anything you do should be according with our mandate. So it's all over the place. There's no universal agreement, and that's important that we do. So let me just come to the conclusions. Last slide. Yeah, so artificial intelligence is definitely, in my opinion, going to change the way we use computers. We might become more productive writers, for example. They might be able to help us solve big problems. I'm completely sure that, for example, detection of disease, detection of images that do, for example, radiographies, the amount of data we can use now can help us train to detect all kinds of disease. I know that a company in Germany has been very, very successful on detecting several types of retinopathies, I mean the eyes diseases. But I already mentioned several mathematical questions and problems that we have when we don't have enough data. Just mathematical, technical questions. But then there's also the issue of the ethical questions, right? If we are failing these ethical questions, even if you have the best of mathematical tools, you are going to be in big trouble. So I think at the moment, we are in a very strange historical moment. I think we have a combination of fear and excitement, I say, fear and excitement. And I think we need to, right now, this is a good historic moment to try to create some kind of agency or maybe a group of agencies that are going to regulate or start regulating what it means to do proper or humane artificial intelligence. That is going to be good for humans. It's not going to be biased. It's going to be equitable access to these AI tools. Yes, I ran out of space here, but yeah. So we likely need to regulate many of these things. I don't know if you know that in California there is one new initiative in the legislation for the California legislation that is saying that in the future the consumers need to know why AI declined their loans. This is very important. So because many times the data is biased and declines the loans of minority groups more often than not, right? So there has to be some kind of explanation of why this is happening in such a large numbers, right? I think these kind of consumer protection laws, we can think of this as consumer protection laws, should be part of the... Now, we need also savvy consumers. And that is exactly UC Davis' job. So I claim that we should not shy away from using ChatGPT in our classes. In my opinion, what we should do is actually discuss this openly with the students. In math classes, for example, I see my colleagues, they were sending emails about how students are using ChatGPT to write math proofs, and they are wrong often. They're very, very, very wrong. But we need to train the students to not trust these things, right? Teach them how all these kinds of issues that there's in the software. The regulation will have to take into account the biases, privacy, intellectual property in the new age, right? It's not anymore intellectual property the way my grandparents thought about intellectual property. Now we have all this appropriation of images, sounds. Your voice is now maybe can be captured and replicated. And I run out of space here, but I'm not so much worried about a killer machine coming soon, but I'm more worried about a corporation making profit out of these types of tools without any regulation. I think I'm much, much more worried of that happening sooner than the Terminator. And with that, I want to end my presentation. Thanks for your time.
Thank you. Questions, and I'd love to hear from the students. I'll take this one, but next a student.
Okay, student first.
Okay, student first. Yeah, you go and then think questions because.
So Jesus, we have students using ChatGPT for writing something. Could we have Professor ChatGPT to check the probability that this was written by something? Because it's just taking stuff that's available on the web. If we as humans, we don't have access to all this stuff, but Professor ChatGPT will have that access.
Yeah, I think already we see tools being developed that are, battling back technology abuses with technology. For example, I just saw that recently a company has produced this thing that actually checks is this human generated or is this they're aiming to do that in text, for example, and apparently this has certain success. I think that yes, that will happen, that is happening, but that might not be enough in my opinion, because we don't know other things. The technology is so fast moving that I don't think anybody can be 100% sure that they caught the right thing. I mean, I have also I'm aware that sometimes they get the wrong answer, right? The people that say, oh, this is artificial. No, it's not artificial. It's actually human writing this way. It's a little bit, yeah.
This is back to the chihuahuas and the muffins. A lot of the work in the, machine learning realm that I've been listening to recently is all about like manifold learning and intrinsic dimension of the data that you're looking at. And what you stated, I guess, is if you have twice the overall dimension, then you think you can find this logistic map will work or the logistic model will work. Have you looked into how that relates to these ideas of intrinsic dimensionality, and do you think that would be fruitful?
Yeah, thank you. Yes, this is one of the simplest examples I could choose, but we have looked at other more complicated models where there's, in some sense, more understanding. The geometry is more complicated. So let me give you just one notch harder than what I show you. Imagine that you are not doing logistic regression. You not only have chihuahuas and muffins, but you have, faces of, pictures of chihuahuas, cats. So multi-classification. You have M classes that you need to classify. Then the conditions are more complicated already, and we understand how many times to sample. In that case as well, we have some thresholds for sampling and make sure that the model is correct or properly applicable. But yeah, there's more to do, and it's nice to.
So you were basically mentioning the classification problem, but I want to ask, how do we interpret the fine-tuning, like few shots, those technique? We usually need like 1 or 2 images or a few articles that then we can get the same style of the image. We can like output that kind. How do we interpret that? Like we only need very small data and we can get a quite useful model.
Yes, I don't understand. I mean, that's fascinating to me. That's a great question. I don't understand why some problems you need very sparse data and then you do great predictions or you do great replication, so to speak. Is a puzzle to me. I think this is something we need to understand, and I don't think many people understand. Anybody understands it really well. So there's a lot of researchers working on that, I think. But typically what has happened is that for image and voice generation, they use already, you're right, I mean, they use very small sample size and they can do, wow, this is exactly the same. You cannot tell apart the Picassos, right? This is really a Picasso. Yeah. Yeah.
So I'll take ownership of the mic and ask my own question. I really liked your framing, I think back in the logistic function part of your talk, where you were saying when the model fails to converge, I think was the word
right.
you used, then it turns out things are just made up, more or less.
Yeah.
And you see that with ChatGPT. One of my favorite tricks is you ask it to write a biography of you, and then you're like, that's all wrong, but it's in the right direction. So it clearly just made stuff up.
Right.
But what do you think? So I would love. What do you think is the possibility from a more conceptual or theoretical perspective that we can detect failure to converge and indicate that when the answer is given, like a red bar saying ChatGPT is probably full of it, or actually,
yeah.
you might take this more seriously.
Yeah, that's a great question. I don't know. Right now, all the conditions we have for when is my data correct, I only have really exact criteria,
yeah.
which don't allow for this kind of, this is probably 80% correct, or this is not correct at all. Right? Yeah, I don't think we have the understanding of when are models legally usable, enough knowledge of that to apply it to certification or to say this is not correct or likely not correct.
Yeah, if only we could develop that for people.
Right.
Yeah. Okay. There's a recording, so it's better.
So this is similar to one of the earlier questions, but so you mentioned that now we get these videos of Obama saying something crazy, we get these fake Picassos, but this isn't a totally new thing, right? I mean, there's been, in the past, governments will scrub a photo to remove a person who's no longer in the favor of the government, right? And then put that photo out to the public. People think maybe this person was never in the photo. From your position studying this kind of stuff, what do you think the future looks like? Do you think that, I guess, similar to how I was asked earlier, the technology to figure out, in particular, things presented as evidence, things like this is a video of a crime scene, this is a this is an image of a politician doing XYZ. Do you think the technology to detect whether those images or recordings are fake or not will keep up with the technology to create fake evidence? And then also, in either situation, whether or not the technology keeps up, what do you think is going to happen with that kind of stuff being passed off as fake? Because maybe the technology can keep up, but the average person doesn't have that. You have to trust someone to tell you whether or not it's real.
Yeah, as I mentioned before, I don't think the technology to prevent misinformation, let's say catch misinformation fast enough, is keeping up for sure. And companies such as, just to compare these, companies such as, well, in the old Twitter at least, right? In the old, before Elon Musk took over, there was a lot of concern, or Facebook, for example, there was a lot of concern of removing misinformation or removing actually even hateful speech and things like that. And this is really dangerous, that you also have corporations, companies just saying, oh, this is not important anymore. Let's just, it's a free-for-all. Because now that if it is a free-for-all, you have the additional amplification of the problem that comes because you have, everybody has access to technology that fake the face of Obama. Then you have not one or a couple of very sophisticated videos. You have thousands and thousands of videos coming every day. And that is the real danger. So yeah, I think that we cannot keep up. You are inundated by so much misinformation or wrong information that then nothing is working. The framework of trustworthiness is being broken in some sense. Yeah.
All right. Any other questions? Okay, then let's thank our speaker. And do you want to?
So if the three speakers would like to come to the